So, welcome to lecture 3 essentially. So, the last time what we did was that we started the thermodynamics of the multiphase systems and we considered that what is the stability and the equilibrium criteria. We went through the Gibbs phase rule and we identified some related parameters, the degree of freedom of a system. This time we are going to go into a little bit further, and so first we will start with Maxwell equation or the Maxwell relations. Okay. Now, for reversible process in a single component, we are still in the single component, we have not gone into the multi-phase multi-component part as of now. For a single component system, the internal energy change is given by TdS minus PdV. This we already did. Similarly, there are varieties of other forms by which we can write essentially the same expression, represent the same thing essentially, TdS plus VdP. This is written in terms of the enthalpy. Similarly, you can write it in terms of the Helmholtz free energy. Sorry. Minus VdV and the Gibbs free energy as well. So, minus SdT plus VdP. So, these are the equivalent forms. Okay. Now, if you look at all these forms, they all have a generalized format which is given as this. Okay. So, this is basically what we call the total differential of Z, the total differential of Z, right. Okay. So, now, if you write it like this, see all the forms exactly has that particular format. So, if we write it properly, the M, okay, can be written as dZ by dx given constant y, N is given as dZ by dy at a given x, right. Remember that dZ is an exact differential. Okay. So, from this particular expression, this is the way that we can write. So, in general, from this what we can say is that the partial of M with respect to y at a constant x and the partial of N with respect to x at a constant y, they must be the same and they are both equal to this. Okay. Now, using this format, okay, we can basically cast all the equations and we can derive some handy relationships which are basically called the Maxwell relations, is equal to, for example, minus dP by ds at constant V. So, you can see we have 4 fundamental equations and we have this relationship that we can write. Okay. So, each of this is like a Z, this, these are like DZs. Okay. So, just by using that combination, okay, we can write, say for example, the first one that we have written, okay, dt by dV at constant S, because this is at a, this is ds if you see this particular relationship, and this is dP by ds at constant V. So, from this expression we can write this. Okay. So, that is the first Maxwell relations. Okay. Similarly, you can write it as dt by dP at constant S is equal to dV by ds at constant P. Okay. So, that is the second relation that you can get out of this. Okay. So, you just have to assume that this is your M, this is your N, and then you have to correspondingly apply this particular form. Okay. So, then you will get these relationships. Similarly, from the last two equations we can get ds by dv at constant t is equal to dp by dt at constant v, and the last form. So, that is comes from this equation now, this particular form, and the last form is ds by dp at constant t is equal to minus dv by dt at constant v. So, these are the four Maxwell relations that we can derive out of the four fundamental equations, okay, and for reversible process obviously, and using this kind of a total differential form. Okay. So, the Maxwell equations is particularly useful, okay, because if you want to develop the relationships between quantities, there are certain quantities, for example, which you cannot even measure. Okay. So, to cast that particular quantity in terms of something else is very, very important. For example, entropy is something that you may not be able to measure, right, take this particular relationship, but you may be interested in knowing the variation of entropy with volume, right, at a constant temperature. But if you can cast it in terms of pressure and temperature differential, right, which is there on the right hand side, both of these two terms are actually measurable. Okay. So, you can get the variation of entropy say with volume at constant temperature by measuring something else. Okay. So, that is the part that is of vital importance over here, right. Okay. At the same time, so similar such expressions, if you want to get the variation of entropy with pressure, say for example, you just measure the change of volume with respect to temperature at a constant P. Okay. Similar things are available in all other cases. Some are experiment, for example, some quantities you can measure experimentally, some quantities you may not be able to measure experimentally, but you may be interested in knowing the variation of those quantities. So, this is the platform which actually gives you something similar to that. Okay. So, that is the first thing that we have done over here. So, the Maxwell relationships are therefore very important and will come in handy as we move on into the later parts of these courses. Okay. Now, let us start bringing now the compositional changes in the system. So far we have done like single phase, single component, we have done that when you have multi phases, how many degrees of freedom do you require. Now, let us see a multi component framework as well. So, let us start with a closed system, okay, with compositional change. Okay. So, the closed system with compositional change. Now, normally the internal energy will be a function of only two quantities, right. This is for single phase, single component. This we already know. This is for single phase, single component. Okay. But what happens when we actually have a compositional change over here? That means your energy now will be now a function of S V comma N 1, N 2 da 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 up to N n, okay, where these represents the number of moles of each of the n components. Understood? So, that means now the internal energy is not just a function of two independent properties, in this case entropy and volume, it is also a function of the different moles of the individual components that are present in the system. Okay. So, and this is a closed system if you recall. Okay. Now, if I do a total differential of this, you can guess that this will be the first term, correct. The second term will be, as you can guess, this is very standard S comma Ni at constant V, right, is differential with respect to V. And lastly, now you have a summation 1 to n dE by dNi right. This is for constant S, constant V, and N, constant N, where N is not equal to Nj is not equal to Ni. Okay. So, that is, this is for the constant composition part. Composition, and this is the effect of multiple components. Okay. This is the effect of multiple components, right. Okay. Now, from our own knowledge of things, we already know that this V comma Ni is equal to T, right, and similarly S comma Ni is equal to minus P, right. So, these are the this term and this term essentially, right. Okay. So, these two terms we know the nature of this, that is the variation of energy, the internal energy with entropy for a constant volume and the constant number of moles of the, or a fixed given configuration of the number of moles of the components is basically nothing but temperature, whereas this particular term is nothing but the negative of the pressure. So, what about this particular term, right, that is the most important part, right. So, this particular part is nothing but something called a mu I this is basically called the chemical potential. The fancy name of this is the chemical potential. This is the chemical potential of the ith component essentially, right. So, that is the summation of all the chemical potentials. Okay. So, for a multi-component system in general, your dE is written as TdS minus PdV, right, plus summation I equal to 1 to n mu I dNi, that is what it is, right. Okay. Where mu I is called the chemical potential of ith component, correct. So, this part should be quite clear that what we have done is that only other thing that has come into the picture is this term mu I or the chemical potential. Why that has come? That has come because the number of moles, it is no longer a single component system. That means it is not, for example, if you deal with this room, say for example, a room, okay, just the room, your bedroom, living room, whatever it is, right. Now, that particular room, what you will find is that it is composed of air, right. Now, air normally, though it is multi-component, sometimes we take it as a single component system, okay. But on the other hand, if you take say a combustor, right, a combustor in which you put fuel, right, you put oxidizer, and at the end of the day, if it is a closed system, okay, so it is like a vessel, you burn this two and you get the products, okay, like CO2, CO and other things. Okay. So, this is a perfect example of a multi-component system, right, because you have fuel, okay, you have air, you have the oxidizer which is normally air, you have the products like water, CO2, CO, oxides of nitrogen, etc., whatever. Okay. So, this is a perfect example of a multi-component system. Now, to analyze that particular problem, you need to see that the change in internal energy of the system is not just given by the temperature and the pressure, I mean the first two terms, right. It is also given by the chemical potential and the number of available moles of each of the component. Okay. So, that is the expression that we kind of developed in terms of internal energy. Now, similarly, there may be other representations also. So, this is one representation. other representations also, in which you have, say for example, dH, which is basically nothing but the enthalpy, plus TdS plus summation, again I equal to 1 to n mu I dni. Okay. Then you have dF, which is given as minus S dt minus P dV plus summation I equal to 1 to n mu I dni. dG on the other hand is written as V dP minus S dt plus summation I equal to 1 to n mu I dni. Okay. So, these are the other equivalent representations that are actually possible. Okay. So, the mu I therefore can be written in a variety of forms, right. So, it can be written as dH dni for constant P, constant S. These are all equivalent representations, right. This is also the same as dF dni, Tv ni not equal to j, right. This is also equal to dG by dn dni, okay, for T, P, Nj not equal to I. So, all these are possible representations, okay, for the same thing essentially. So, all the chemical potential is a term. Now, that chemical potential can be represented in these varieties of ways, right. Okay. Now, so we have seen in a multi-component system essentially the thing is still the same, but except that we have this additional term which enters into the picture. Now, let us look at a multi-phase system now. Okay. So, to do that, first multi-phase system, what happens in multi-phase systems and what is the similarity between that and a multi-component system, we will just look at it. In a multi-phase system, say it has a single component for simplicity. A multi-phase system, as I told you in the first lecture, it can be of multi-component nature as well. Okay. Now, in a multi-phase system, we can write the same internal energy as Tk K equal to 1 comma 2, where 1 and 2 are basically the two phases. K is basically the phase. It can be 3 phases also. Right now, we have just chosen 2 just for the purpose of simplicity. Okay. So, for a multi-phase system, the internal energy change of the kth phase is actually given by this expression, where mu k is basically the chemical potential of the kth phase. That sounds awfully similar to the multi-component system as well, right. For the multi-component system, we have something very equivalent like this. Okay. Also, whether k equal to 1 to 2, you have dSk, which is basically the change in entropy for constant energy and constant volume is equal to 0, correct. So, the change in entropy for constant energy, internal energy and constant volume is actually equal to 0. Okay. So, since of the reason that the two phases E and V are, since E and V are constant, the change in internal energy of the two phases must also be equal to 0. So, let us go to the next page and write that since E and V are constant, right, okay, the change in internal energy okay, of the two phases must be 0 as well. Okay. So, that would mean that dE is equal to sum total 1 to 2 dEk is basically equal to 0. Also dV which is equal to k equal to 1 to 2 dVk is also equal to 0. Okay. Since the system is closed, because we are dealing with closed system is closed, okay, the dN, which is basically nothing but summation of k equal to 1 to 2 dNk, that is also equal to 0. That is the number of moles of each of the phases, that is also equal to 0, right. So, no change in the number of moles, the total moles resulting from the two phase changes, right, essentially that is what it means. Okay. So, these are the three statements that you get, and the last one I wrote it in the previous page. Okay. So, if you combine all of these things together, so you combine the change in entropy is equal to 0, the change of internal energy is equal to 0, the change of volume is equal to 0, and the change of total number of moles is equal to 0. If you combine all of them, ds is equal to 0 essentially. This means 1 by T1, T1 and 1 and 2 are the two phases, say for example, as that we already mentioned, dE1 plus P1 by T1 minus P2 by T2 dV1 minus mu1 by T1 minus mu2 by T2 dN1, right, correct. Now, since this, for the equilibrium to exist between the two phases of a single component, we can see that these are any variations of V, N and all those things, right. So, the sum total of all these terms are actually equal to 0, correct, but this variation can be anything, right, dV1, E1, okay, dN1, right. So, that would mean in order for the sum total of these terms to be equal to 0, individually these terms should be equal to 0 as well, right. So, from the first expression we get T1 is equal to T2, right. Since T1 is equal to T2, from the second one we get P1 is equal to P2, right, and from the third one we get mu1 is equal to mu2, right. This is valid for any two phase systems, right. So, the important conclusion that we have drawn out of here is as follows. We have combined this and we have shown that for a closed system, okay, you have the temperature between the two phases should be the same. So, the two phases, for the two phases to exist in equilibrium, right, this is for two phases in equilibrium, two phases in equilibrium. Okay. When the two phases are in equilibrium, the temperature between the two phases should be equal, the pressure in the two phases should be equal, and the chemical potential between the two phases should also be equal, correct. So, that gives us, so this is valid for any two phase systems, okay, which are in equilibrium with each other, that you can show through extrapolation and you can show through other methodologies as well, that this entire thing that we have shown, these are important parameters that we have shown that the chemical potential is equal across the two phases, right. Okay. So, that is an important observation. Okay. So, for a single component two phase systems, we have seen what is a criteria for the two phases to exist in equilibrium. Now, let us look at another important thing which also is you have encountered. This is called the Claeyron equation, right. We will find the utility of these equations when you go to the droplet and other type of phenomena, right. Now, in the Claeyron equation what happens is that, let us put the statement, if the temperature of a two phase system is slightly changed, right, changed. That means the systems were in equilibrium, the temperature is slightly changed, the pressure will be obviously affected, right, the pressure will be affected, right. So if the pressure is affected, okay, then what is the simple relationship between the temperature and pressure? Okay, if I have a change of temperature and a change of pressure, how these two things are kind of related when the two phases are in equilibrium to each other, right. So, I will not do the derivation, okay, but the general form of the Claeyron equation the derivation you can look up your undergraduate books, okay, it should be there, and I will explain what each and every term actually means. So, the change or the slope, the change in pressure and the change in temperature, okay. So, essentially it is a slope, okay. The slope is related to, that means this is the relationship between pressure and temperature, this is related to the latent heat of the phase change. That means the phase changes from 2 to 1 or 1 to 2, whatever that may be happening. Okay. So, it is the latent heat due to the phase change, and this one is the change in specific volume during phase change. Okay. So, this is a unique relationship, that means that if you know the latent heat of phase separation and if you know the phase change, the specific volume change during the phase change, and if you know the temperature at which the phase change happens, the change in pressure and the change in temperature can be related to each other, right. Okay. Now, several relationships among temperature, pressure, volume and the enthalpy change for a single component system exists. But the two phase system at equilibrium actually obeys a form like this, right. Now, for a liquid vapor system, now this is valid for any system, right. This for a liquid vapor system specifically, dP by dt is given by HLV, in that case 1 and 2 are the liquid and the vapor, right, that is given by Vb minus Vl, right, and this is given by the T saturation, right. So, the T saturation is what it is. So, this particular relationship is the same, but with a little bit of a change, except that this is now the latent heat of vaporization essentially. Okay. Now, Vl is the specific volume of the liquid, right, specific volume of the liquid, and Vb is the specific volume of the vapor, right. Now, normally because of expansion, okay, the Vb is normally much greater than Vl, right, that is obvious, because you take a small drop of water and if you expand, if you just vaporize it, okay, because of the severe density change, because this is nothing but the inverse of the density change, the specific volume, right, the vapor expands almost like 1000 times, right. So, you have 1000 time change in volume just for, say for example, for water. Similar happens for other types of fluids as well, right. So, and this Vb you can also write it, you can consider this as an ideal gas and you can write it in this form as well, right. So, considering that this is an ideal gas is something which is basically you can disregard any compressibility effect, okay, in the ideal gas. So, this dP by dt is given as HLV, okay, HLV into P divided by Rg T square, right. This particular form is called the Clausius-Clapeyron form, got it. So, this was the Clausius equation, this particular slightly revised form is called the Clausius-Clapeyron equation, clear on this particular part. So, this is perhaps, so at this particular point what we have done is that we have just applied the ideal gas law assumption and the fact that the density of the vapor is much less than the density of the liquid. That means the specific volume of the vapor should be much higher than the specific volume of the liquid, and I gave you the example of water and water vapor, right, where you do get about 1,000 times change in the volume. Okay. So, after this what we are going to do, and we will just introduce the problem over here and we will continue in the next class. So, the first thing that we will do over here is that now that we know that what is the relationship between temperature and pressure when there is a phase change happening, and when the phase actually is in equilibrium to each other, what are the conditions that are needed. But one important thing that I told you in the first lecture was that what about the interfaces? We have to know the thermodynamics of the interfaces. So, I will just introduce the thing over here and go into the next lecture, thermodynamics at the interfaces. Okay. So, what is thermodynamics of the interface? Let us look at the interface. For example, if this is a droplet of liquid, a raindrop say for example, this is the ambient, So, what happens is that this liquid and the ambient is separated basically by this interface, right. Similarly, you can have a bubble. We all have seen if you blow a bubble, okay. So, that is also, you can blow a bubble inside a liquid also. So, you can see that there is an interface which is separating the two phases, right. And we, the first class we said that this can be a nice geometric interface, it can be like a corrugated interface, it can be a lot of things. Okay. Now, this interface can be thin interface or it can be a thick interface also. So, there can be, so if we zoom in into the interface, perhaps you will see something like this. This is bulk fluid 1, this is say bulk fluid 2, okay, and the interface is dividing surface. Okay. It's like a dividing surface, an arbitrary function, whatever you call it, okay, and that interface is mentioned as something like an I. Okay. So, the two bulk fluids, so this can be liquid vapor, vapor liquid, whatever, solid vapor, whatever you can think of, okay, they are separated by an interfacial region basically, it is like an interfacial region. Okay. So, this interfacial region can be very thin. In most of the cases we consider it to be very thin, but we still need to know that what is the mechanism by which mass or heat transport occurs from this to this, right, through the interface, right. That is a most important thing that will affect all the calculations that you see over here. Okay. Here of course, the two phases are not mixed with each other, okay, but it is basically also can be considered as a single substance which has two phases. That means, fluid 1 is the same, is a different phase of the same substance like water and water vapor. Okay. It can be actually many things. It can be two immiscible liquids, it can be a single substance with two phases, it can be a mixture of gases in contact with a solid surface, or it can be also be a chemically reacting interface. Like for example, this can be a flame. If you look at a flame, okay, a candle flame for example, or any other flame, okay. So, one side is oxidizer, okay, one side is a product, right. There is an interface which basically separates the two, okay. Though these are of two different components, there may be two different phases also that can be present, okay. So, all these are interfacial phenomena which we need to know that how this interface actually behaves. So, next class what we are going to try to establish is that what is the thermodynamics of this particular interface, okay, whether this interface is kind of a nice interface and what kind of a transport can happen, okay, what is the what are the equations that are valid across the interface. For example, if this temperature is T1, this temperature is T2, the interfacial temperature is Ti, what is the relationship between temperature T1, T2 and Ti, what is the relationship between them, right. Also, what about the chemical potential, that means mu 1, mu 2, mu I, right. So, we need to know that how those chemical potentials actually vary. Okay. So, this is the thing that we have. So, these are the interfacial phenomena. In the next class we are going to see that how these interfaces actually vary, okay, how these interfaces can be described.